Right now, as you're watching this video, there are particles inside your body that are so incredibly tiny that if you tried to line them up side by side, you could fit more of them across the width of a single atom than there are atoms in the entire observable universe. But here's the mind-bending part. We might have just discovered that these aren't even the smallest things that exist. I'm talking about the fundamental building blocks of reality itself. The things that make up literally everything you can see, touch, and experience. For centuries, humans have been asking the same question. What happens when you keep breaking things down into smaller and smaller pieces? Where does it end? And the answer we found is so strange and counterintuitive that it challenges everything we think we know about the nature of existence. Today, we're going deep into the quantum world to explore the smallest scales of reality. And I promise you, by the time we're done, you'll never look at the world around you the same way again. Here's the thing that keeps physicists awake at night. We live in a world where everything seems solid and predictable. You drop a ball, it falls down. You push a wall, it pushes back. But when you zoom in far enough, when you get to the scale we're about to explore, all of those rules completely break down. The problem is this. We've built our entire understanding of physics on the idea that things get smaller and smaller until you reach some kind of fundamental, indivisible particle, like building blocks that can't be broken down any further. But every time we think we found the smallest thing, we discover it's made of even smaller things. And then those smaller things turn out to be made of even smaller things. It's like peeling an onion, except the onion has infinite layers, and each layer operates by completely different rules than the layer above it. And just when you think you understand those rules, you discover that the very act of trying to measure these tiny particles changes them in ways that seem impossible. This isn't just an academic problem. The quest to understand the smallest scales of reality has led to some of the most important discoveries in human history. The computer you're watching this on, the GPS in your phone, the medical imaging that saves lives every day, all of these technologies exist because we've learned to work with the bizarre rules that govern the quantum world. But here's what's really crazy. The deeper we dig, the more we realize that our everyday experience of reality might be nothing more than an illusion created by the collective behavior of trillions upon trillions of these impossibly small quantum entities. It's like discovering that what you thought was a smooth painting is actually made up of countless tiny dots when you look at it under a microscope. So let's start this journey together. We're going to travel through scales of size that are almost impossible to imagine. We'll meet particles so small that the word small loses all meaning. We'll explore forces so fundamental that they shape the very fabric of space and time itself. And we'll discover that at the smallest scales of reality, the universe operates more like a cosmic video game than the solid, predictable world we think we live in. Part 1. The scale of smallness. Before we can understand just how small we're talking about, we need to wrap our minds around the scales involved. This is where most people's brains start to hurt. So I'm going to take you through this step by step using comparisons that actually make sense. Let's start with something you can relate to. Take a penny. Now imagine you could shrink yourself down until that penny looked as big as the entire Earth. At that scale, the atoms in the penny would be about the size of marbles. That's already pretty tiny, right? But we're just getting started. Now imagine you could shrink down even further until one of those marble-sized atoms looked as big as a football stadium. At that scale, the nucleus of the atom, the dense center where most of the atom's mass is concentrated, would be about the size of a marble sitting in the middle of that stadium. Everything else is just empty space. This is the first mind-bending realization about the quantum world. Atoms, which make up everything around you, are almost entirely empty space. If you could somehow remove all the empty space from the atoms in your body, you would be compressed down to a size smaller than a grain of sand, but you'd still weigh exactly the same. But we're still not at the smallest scales. Those marble-sized nuclei in our stadium-sized atoms are themselves made of even tinier particles called protons and neutrons. And here's where things start to get really interesting. For most of the 20th century, scientists thought protons and neutrons were fundamental particles. They couldn't be broken down any further. Then, in the 1960s and 70s, we started smashing these particles together at incredibly high energies, and we discovered something shocking. Protons and neutrons aren't fundamental at all. They're made of even smaller particles called quarks. Now, quarks are weird, really weird. They come in 6 different types that physicists, in their infinite creativity, decided to call flavors. These flavors have names like up, down, strange, charm, bottom, and top. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. It's like a cosmic recipe book where different combinations of ingredients create different types of matter. But here's the truly bizarre part about quarks. You can never find one by itself. They're always bound together in groups. It's like they're cosmically shy and refuse to be alone. If you try to pull quarks apart, the force holding them together actually gets stronger the farther apart you try to pull them. It's the opposite of what happens with magnets or gravity, where the force gets weaker with distance. Imagine if you had a rubber band that got stiffer and harder to stretch the more you pulled on it, until eventually it became impossible to stretch any further. That's what the force between quarks is like. Scientists call this confinement, and it's one of the most mysterious aspects of quantum physics. So, are quarks the smallest things? Well, as far as we can tell with our current experiments, yes. Quarks appear to be point particles with no internal structure. But here's the thing. We thought the same thing about atoms, and then about protons and neutrons. Every time we've built more powerful microscopes and particle accelerators, we've discovered that what we thought was fundamental actually had parts. This raises a fascinating question. Is there a bottom to this cosmic onion, or does it go on forever? Some theories suggest there might be even smaller structures inside quarks. Others propose that at the smallest scales, our very concept of size breaks down completely. The quantum revolution. To understand why the quantum world is so strange, we need to go back to the beginning of the 20th century, when physicists first started to realize that their understanding of reality was completely wrong. It all started with something called the ultraviolet catastrophe. Scientists were trying to understand how hot objects give off light. According to the physics of the time, when you heated up a piece of metal, it should give off infinite amounts of ultraviolet light. But obviously, that doesn't happen. If it did, every hot object would instantly vaporize everything around it with deadly radiation. A German physicist named Max Planck solved this problem in 1900 by proposing something radical. He suggested that energy doesn't come in smooth, continuous amounts like water flowing from a tap. Instead, it comes in tiny, discrete packets that he called quanta. It's like energy is made of Lego blocks. You can have 1 block, or 2 blocks, or 3 blocks, but you can't have 1.5 blocks. This might not sound revolutionary, but it completely overturned our understanding of reality. It would be like discovering that you can't pour any amount of water you want from a pitcher. Instead, water only comes out in specific, tiny droplets, and you can only have exact numbers of droplets, never anything in between. Albert Einstein took this idea even further in 1900 1905 when he explained something called the photoelectric effect. He showed that light itself is made of these quantum packets, which we now call photons. This was shocking because everyone knew light was a wave. You could demonstrate this with simple experiments that showed light behaving exactly like waves in water. But Einstein's explanation required light to behave like particles, little packets of energy bouncing around like tiny billiard balls. How could light be both a wave and a particle at the same time? This paradox would haunt physics for decades. Then, in the 1920s, a young French physicist named Louis de Broglie proposed something even more radical. If light, which everyone thought was a wave, could behave like a particle, then maybe particles, which everyone thought were solid little balls, could behave like waves. This led to one of the most famous experiments in physics, the double-slit experiment. Here's how it works. You take a barrier with two parallel slits cut into it, and you shine light through it onto a screen on the other side. What you see is a pattern of bright and dark stripes, which is exactly what you'd expect if light was a wave. The waves from the two slits interfere with each other, creating areas where they add up, bright stripes, and areas where they cancel out, dark stripes. But here's where it gets weird. When you send light through one photon at a time, literally individual particles of light, you still get the same wave pattern. Each individual photon somehow knows about both slits and interferes with itself to create the pattern. But wait, it gets weirder. If you try to detect which slit each photon goes through by placing a detector at one of the slits, the wave pattern disappears completely. The photons stop behaving like normal particles, each going through one slit or the other. It's as if the very act of trying to measure where the photon goes changes its behavior. This isn't just true for photons. You can do the same experiment with electrons, atoms, and even large molecules. Everything in the quantum world exhibits this bizarre wave-particle duality, and everything changes its behavior when you try to measure it. This leads us to one of the most fundamental principles of quantum mechanics, the uncertainty principle, discovered by Werner Heisenberg in 1927. The uncertainty principle says that there are certain pairs of properties that you can never measure precisely at the same time. The more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This isn't just a limitation of our measuring instruments, it's a fundamental feature of reality itself. At the quantum level, particles don't have definite positions and momenta until you measure them. Before measurement, they exist in a superposition of all possible states simultaneously. The Standard Model, our best map of reality, by the 1970s, physicists had developed what we now call the Standard Model of particle physics. Think of it as the most successful theory in the history of science. A cosmic parts list that describes all the fundamental particles and forces that make up everything in the universe. The Standard Model divides particles into two main categories, fermions and bosons. Fermions are the matter particles, the stuff that makes up atoms and everything we can touch. Bosons are the force particles. They carry the forces that hold everything together or push everything apart. Let's start with the fermions, because these are the building blocks of everything you see around you. There are 12 types of fermions divided into two groups, quarks and leptons. We've already talked about quarks. Those are the particles that make up protons and neutrons. There are 6 types: up, down, strange, charm, bottom, and top. The up and down quarks are the ones that make up ordinary matter. The others are more exotic and only exist in high-energy environments or particle accelerators. But here's something interesting about quarks. They have a property called color charge. Don't worry, this has nothing to do with actual colors. Physicists just needed a way to distinguish between 3 different types of the same quark. So they borrowed color names: red, green, and blue. Quarks are always bound together in combinations that are colorless. Either 3 quarks of different colors, like red, green, and blue, or a quark and an antiquark of opposite colors, like red and anti-red. This is why you never see isolated quarks in nature. The other group of fermions is called leptons. The most famous lepton is the electron, which orbits the nucleus of atoms and carries electric current in your devices. But there are also 2 heavier versions of the electron called the muon and the tau particle. Each of these has an associated neutrino, the electron neutrino, muon neutrino, and tau neutrino. Neutrinos are perhaps the most ghostly particles in the universe. They have almost no mass and barely interact with anything else. Right now, trillions of neutrinos from the sun are streaming through your body every second, and you don't feel a thing. Most of them pass right through the entire Earth without hitting a single atom. Now, let's talk about the bosons, the force carriers. In the Standard Model, there are 4 fundamental forces, though we've only found particles for 3 of them. The electromagnetic force, which includes both electricity and magnetism, is carried by photons. These are the same particles that make up light, radio waves, X-rays, and all other forms of electromagnetic radiation. The weak nuclear force, which is responsible for certain types of radioactive decay, is carried by particles called W and Z bosons. These are much heavier than photons and have very short lifetimes, which is why the weak force only operates over tiny distances inside atomic nuclei. The strong nuclear force, which holds quarks together inside protons and neutrons and holds protons and neutrons together inside atomic nuclei, is carried by particles called gluons. Gluons are massless like photons, but unlike photons, they carry color charge themselves, which makes the strong force behave in very unusual ways. The 4th fundamental force is gravity, and this is where the Standard Model runs into trouble. We haven't been able to find a particle that carries the gravitational force, though physicists have given it a name, the graviton. The problem is that gravity is incredibly weak compared to the other forces. It's so weak that we've never been able to detect individual gravitons, even though we're constantly surrounded by gravitational fields. To give you an idea of how weak gravity is, consider this. It takes the entire mass of the Earth to keep you from floating away, but a small magnet can easily overcome Earth's gravitational pull to pick up a paperclip. The electromagnetic force is about 1 trillion times stronger than gravity. But the Standard Model includes one more particle that's absolutely crucial to how everything works: the Higgs boson. This particle is associated with something called the Higgs field, which permeates all of space. The Higgs field is responsible for giving other particles their mass. Here's how it works. Imagine space is filled with a thick cosmic molasses. That's the Higgs field. As particles move through this field, they interact with it in different ways. Some particles, like photons, don't interact with the Higgs field at all, so they remain massless and always travel at the speed of light. Other particles interact strongly with the field, which slows them down and gives them mass. The discovery of the Higgs boson in 2012 was the culmination of a search that lasted nearly 50 years. It required building the largest, most complex machine ever constructed by humans, the Large Hadron Collider at CERN, which cost over $10 billion and involves collaborations between thousands of scientists from around the world, going beyond the Standard Model. Even though the Standard Model is incredibly successful, it's made predictions that have been confirmed to incredible precision. We know it can't be the complete picture. There are several major problems that the Standard Model can't explain. First, there's the mystery of dark matter. Astronomical observations tell us that about 85% of all matter in the universe is made of something that doesn't interact with light at all. We can see its gravitational effects on galaxies and galaxy clusters, but we can't see it directly. None of the particles in the Standard Model could account for dark matter. Second, there's the problem of dark energy. Observations show that the expansion of the universe is accelerating, driven by some kind of energy that fills empty space itself. The Standard Model has no explanation for what this could be. Third, the Standard Model doesn't include gravity. While gravity is extremely weak and usually ignorable at the quantum level, we know that at the smallest scales, much smaller than anything we've discussed so far, quantum effects of gravity should become important. We need a theory of quantum gravity, but despite decades of effort, we don't have one yet. This has led physicists to propose various extensions to the Standard Model. One of the most popular is called supersymmetry, or SUSY for short. Supersymmetry predicts that every particle in the Standard Model has a superpartner, a heavier version with slightly different properties. These superpartner particles could potentially explain dark matter. Another extension is string theory, which proposes that the fundamental constituents of reality aren't point particles at all, but tiny vibrating strings. Different vibration patterns of these strings would correspond to different particles. String theory naturally includes gravity and could potentially unite all the fundamental forces into a single framework. But string theory makes a startling prediction. It requires extra dimensions of space. While we experience 3 dimensions of space, length, width, and height, plus 1 dimension of time, string theory suggests there could be as many as 11 total dimensions. The extra dimensions would be compactified, curled up so small that we can't perceive them directly. To understand how this might work, imagine looking at a garden hose from far away. It looks like a one-dimensional line. But as you get closer, you realize it actually has thickness. There's a second dimension curled up into a circle around the line. String theory suggests that our 3-dimensional space might be like the line, with additional dimensions curled up in tiny circles at every point. Other theories propose even more radical ideas. Loop quantum gravity suggests that space itself is made of tiny, discrete loops, that if you could zoom in far enough, you'd see that space has a granular structure like a cosmic mesh. At these scales, our normal concepts of distance and time might break down completely. Some theories propose that particles themselves might be made of even smaller constituents. These hypothetical particles have been given names like preons or subquarks. If they exist, they would be to quarks what quarks are to protons, the next level down in the cosmic hierarchy, the Planck scale, where physics breaks down. There's a theoretical limit to how small we can meaningfully talk about the Planck scale, named after Max Planck. This represents the scale where our current understanding of physics completely breaks down. The Planck length is about 1035 meters. To give you some perspective on just how incredibly tiny this is, a Planck length is to the size of an atom what an atom is to the size of a grapefruit. It's so small that if you magnified an atom to the size of the observable universe, a Planck length would be about the size of a tree. At the Planck scale, the uncertainty principle means that the energy fluctuations in empty space become so violent that they can spontaneously create black holes. These virtual black holes would pop into existence and then evaporate almost immediately, but they would completely scramble our normal understanding of space and time. This is where quantum mechanics and general relativity, Einstein's theory of gravity, come into direct conflict. General relativity describes gravity as the curvature of space-time, treating space and time as smooth, continuous entities. But quantum mechanics suggests that at small enough scales, everything becomes choppy and discontinuous. At the Planck scale, space-time itself might have a foamy, chaotic structure, constantly fluctuating and changing. Some physicists describe it as quantum foam, a seething mass of virtual particles and black holes popping in and out of existence. The Planck time, the time it takes light to travel one Planck length, is about 1043 seconds. This might represent the smallest meaningful unit of time. Some theories suggest that time itself is quantized, coming in discrete chunks, just like energy in Planck's original quantum theory. But here's the truly mind-bending part. We may never be able to directly observe the Planck scale. To probe such tiny distances, we would need particle accelerators with energies comparable to the Planck energy, which is about 19 times higher than what we can currently achieve. Building such an accelerator would require more energy than is available in the entire observable universe. This raises profound philosophical questions about the nature of scientific knowledge. If there are scales of reality that are forever beyond our ability to observe, can we ever truly understand the fundamental nature of the universe? Or will there always be deeper layers of reality hidden from us by the very laws of physics themselves, emergent properties, and the bigger picture? Here's where the story takes a fascinating turn. While we've been zooming in to smaller and smaller scales trying to find the fundamental building blocks of reality, something remarkable happens when we zoom back out. At larger scales, new properties and behaviors emerge that weren't present in the individual components. This is called emergence, and it's one of the most important concepts in modern science. Emergence is what happens when the collective behavior of many simple components gives rise to complex phenomena that couldn't be predicted just by understanding the individual parts. Think about consciousness, for example. Your brain is made of neurons, which are made of atoms, which are made of particles following the laws of quantum mechanics. But none of those individual components is conscious. Consciousness emerges from the complex interactions of billions of neurons working together. Or consider the properties of water. A single H2O molecule isn't wet. Wetness is a property that only emerges when you have many water molecules interacting together. Similarly, temperature isn't a property of individual atoms. It's a measure of the average motion of many atoms together. This suggests that our quest to understand reality by breaking it down into smaller and smaller pieces might be missing something crucial. Maybe the most important aspects of reality emerge from the interactions and relationships between components, not from the components themselves. In quantum mechanics, this is called quantum entanglement. When particles become entangled, they become part of a single quantum system, even if they're separated by vast distances. You can't describe the state of one particle without considering its entangled partner. The relationship between them becomes more fundamental than either particle individually. Einstein was deeply troubled by entanglement, calling it spooky action at a distance. He believed that each particle must have its own independent reality, separate from its partner. But experiments have confirmed that Einstein was wrong. Entanglement is real, and it shows us that the quantum world is fundamentally interconnected in ways that our everyday experience can't prepare us for. This interconnectedness might extend all the way up through the scales of reality. The particles in your body were forged in the hearts of stars billions of years ago. The carbon in your muscles, the calcium in your bones, the iron in your blood, All of it was created by nuclear fusion in stellar cores and then scattered across the galaxy when those stars died in supernova explosions. In a very real sense, you are made of stardust. The atoms that make up your body have existed for billions of years, cycling through countless different forms: rocks, plants, animals, other humans. You are a temporary arrangement of ancient particles that will eventually be recycled into new forms after you're gone. But it goes even deeper than that. The quantum fields that give rise to particles permeate all of space and time. In a sense, we're all just different excitations in the same underlying quantum fields. The electron in your brain and the electron in a star on the other side of the galaxy are fundamentally the same entity. They're both excitations in the universal electron field. This raises profound questions about the nature of identity and individuality. If we're all made of the same quantum fields, in what sense are we separate beings? Where does one person end and another begin? These aren't just philosophical questions. They touch on deep issues in quantum mechanics about the nature of observation and measurement. The measurement problem and many worlds. One of the biggest mysteries in quantum mechanics is what happens during measurement. Before you measure a quantum system, it exists in a superposition of all possible states. But when you make a measurement, you always find the system in one definite state. How does the transition from all possibilities to one reality actually happen? This is called the measurement problem. And despite nearly a century of debate, physicists still don't have a universally accepted solution. There are several competing interpretations, each with its own bizarre implications for the nature of reality. The most common interpretation, called the Copenhagen interpretation, simply says that measurement causes the quantum superposition to collapse into a definite state. But this interpretation requires us to draw an arbitrary line between the quantum world, where superposition exists, and the classical world, where everything has definite properties. Where exactly is this line? Why do some systems collapse superpositions while others don't? A more radical interpretation, proposed by Hugh Everett in 1957, suggests that superpositions never actually collapse. Instead, every time a measurement is made, the universe splits into multiple parallel branches, one for each possible outcome of the measurement. In some branches, you measured the particle spinning up. In others, you measured it spinning down. Both outcomes are equally real, but they exist in separate, non-communicating universes. This is called the many worlds interpretation. And if it's true, it means that there are countless parallel versions of you reading this very sentence right now. In some universes, you decided to click away from this video. In others, you're rewatching it for the third time. In still others, this video was never made at all because the particles in my brain happened to arrange themselves differently when I was thinking about quantum mechanics. The many worlds interpretation sounds like science fiction, but it's taken seriously by many physicists because it solves the measurement problem without requiring any arbitrary division between quantum and classical reality. Everything follows the same quantum rules at all scales. It's just that we only experience one branch of the vast quantum multiverse. But if many worlds is true, it raises disturbing questions about the nature of choice and responsibility. If every possible decision you could make is realized in some branch of the multiverse, do your choices actually matter? Is there any meaningful difference between good and evil if every possible action is taken by some version of you? There are other interpretations too. The pilot wave theory, developed by Louis de Broglie and later by David Bohm, suggests that particles do have definite positions and velocities at all times, but they're guided by a quantum field that produces all the strange effects we observe. This interpretation preserves a more intuitive picture of reality, but requires instantaneous, non-local connections between distant particles. The cubism interpretation, quantum Bayesianism, takes a more subjective approach, suggesting that quantum states don't describe objective reality, but rather an observer's subjective knowledge about a system. From this perspective, the weirdness of quantum mechanics comes from trying to treat subjective information as if it were objective reality. Implications for technology and daily life. While these philosophical debates rage on, the practical applications of quantum mechanics continue to revolutionize our world. The quantum properties that seem so bizarre and counterintuitive at the microscopic level enable technologies that we rely on every day. The computer or phone you're using to watch this video only works because of quantum mechanics. The transistors that make up microprocessors rely on the quantum behavior of electrons in semiconductors. Without quantum tunneling, the ability of particles to pass through barriers that should be impossible to cross classically, modern electronics wouldn't exist. But that's just the beginning. We're now entering the age of quantum technology, where we're learning to harness the full strangeness of the quantum world for practical purposes. Quantum computers use the principle of superposition to perform calculations that would be impossible for classical computers. While a classical computer bit can only be in one state at a time, either 0 or 1, a quantum bit or qubit can exist in a superposition of both states simultaneously. This allows quantum computers to explore many possible solutions to a problem in parallel. The potential applications are staggering. Quantum computers could break most of the encryption systems that currently protect our digital communications, but they could also enable new forms of ultra-secure quantum cryptography. They could simulate the behavior of complex molecules, leading to breakthroughs in drug discovery and materials science. They could optimize traffic flow in smart cities, predict weather patterns with unprecedented accuracy, and even help us understand the quantum mechanics of black holes and the early universe. Quantum sensors are already being used to make incredibly precise measurements. Atomic clocks based on quantum transitions are accurate to within 1 second over the entire age of the universe. Quantum magnetometers can detect magnetic fields billions of times weaker than Earth's magnetic field, enabling new forms of medical imaging and archaeological surveys. Quantum communication systems use entanglement to create unbreakable communication channels. Any attempt to intercept a quantum message inevitably disturbs the quantum state, alerting the sender and receiver to the presence of an eavesdropper. China has already built a quantum communication network spanning thousands of kilometers, and other countries are racing to develop their own quantum internet. But perhaps the most profound implications of quantum mechanics aren't technological but conceptual. The quantum world forces us to abandon many of our most basic assumptions about reality. The idea that objects have definite properties independent of observation, the notion that causes must precede effects, the assumption that information cannot travel faster than light, all of these concepts become problematic in the quantum realm. The role of information in quantum mechanics. In recent decades, physicists have begun to realize that information might be more fundamental than matter and energy. This perspective, sometimes called it from bit, suggests that reality emerges from the processing of information rather than the other way around. Consider quantum entanglement again. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. But no matter or energy travels between the particles, only information. The entangled particles share information in a way that transcends our normal understanding of space and time. This has led some physicists to propose that the universe might be fundamentally computational in nature. Maybe reality is like a vast quantum computer, processing information according to the laws of quantum mechanics. The particles and fields we observe might be like the pixels on a computer screen, the visible interface of a deeper computational process. This perspective helps explain some of the stranger aspects of quantum mechanics. The uncertainty principle, for example, might reflect fundamental limits on how much information can be extracted from a quantum system. The measurement problem might be better understood as a question about how information becomes classical and definite. Black holes provide a fascinating example of the importance of information in quantum mechanics. When matter falls into a black hole, what happens to the information it contains? According to general relativity, the information should be destroyed when the black hole eventually evaporates. But quantum mechanics says information can never be destroyed. This contradiction, known as the black hole information paradox, has driven decades of research into the fundamental nature of information and reality. Some proposed solutions to the paradox suggest that information isn't actually destroyed by black holes, but is encoded on the black hole's surface in a holographic form. This holographic principle has far-reaching implications, suggesting that all the information in a three-dimensional region of space might be encoded on its two-dimensional boundary. If the holographic principle is correct, it might mean that our three-dimensional reality is actually a projection from information stored on a distant two-dimensional surface, like a cosmic hologram. This would fundamentally change our understanding of space, time, and the nature of reality itself. Quantum field theory and virtual particles. To really understand what happens at the smallest scales, we need to talk about quantum field theory, the most successful theoretical framework in physics. Quantum field theory describes particles not as little balls bouncing around, but as excitations in quantum fields that fill all of space. Think of it like this. Imagine the surface of a pond on a perfectly calm day. The water represents a quantum field in its ground state, the lowest energy configuration. Now imagine dropping a stone into the pond. The ripples that spread out represent particles. They're excitations in the field caused by adding energy to the system. But unlike ripples on water, quantum field excitations can behave in very strange ways. They can appear and disappear spontaneously, tunnel through barriers, and exist in superpositions of multiple states simultaneously. Even more bizarre is what happens in empty space. According to quantum field theory, what we call empty space is actually seething with activity. Virtual particles constantly pop into existence in pairs and then annihilate each other almost instantly. These virtual particles aren't directly observable, but their effects can be measured with incredible precision. One of the most famous examples is the Casimir effect. If you place two metal plates very close together in a vacuum, the virtual particles between the plates are restricted to certain wavelengths that fit between the plates. But outside the plates, virtual particles of all wavelengths can exist. This creates a pressure difference that pushes the plates together with a measurable force. The Casimir effect shows us that empty space has structure and energy. In fact, the energy density of the quantum vacuum might be enormous. Some calculations suggest it could be 120 orders of magnitude larger than what we observe. This huge discrepancy, known as the cosmological constant problem, is one of the most puzzling issues in theoretical physics. Virtual particles also play a crucial role in the fundamental forces. The electromagnetic force between two charged particles, for example, is mediated by the exchange of virtual photons. These photons can't be observed directly. They exist only for the brief moment it takes them to travel from one particle to another. But without them, there would be no electromagnetic force at all. The strong force works similarly, but with virtual gluons instead of virtual photons. The weak force uses virtual W and Z bosons. Even gravity, if it can be described quantum mechanically, would involve the exchange of virtual gravitons. This gives us a picture of reality where particles are constantly exchanging virtual messengers, creating the forces that hold atoms together, power the stars, and shape the large-scale structure of the universe. These virtual particles are so fundamental to how reality works that without them, there would be no atoms, no chemistry, no biology, and no life. Symmetries and conservation laws. One of the most profound insights in physics is the connection between symmetries and conservation laws. A symmetry is something that remains unchanged under a transformation, like how a circle looks the same when you rotate it, or how the laws of physics are the same everywhere in the universe. It turns out that every conservation law in physics corresponds to a symmetry. The conservation of energy comes from the fact that the laws of physics are the same at all times. The conservation of momentum comes from the fact that the laws of physics are the same at all locations in space. The conservation of electric charge comes from a more abstract symmetry in the quantum fields themselves. This connection, formalized in Noether's theorem, tells us that the fundamental conservation laws that govern everything from chemical reactions to the expansion of the universe are actually reflections of the underlying symmetries of reality itself. But symmetries in quantum mechanics go much deeper than this. The Standard Model is built around what physicists call gauge symmetries, abstract mathematical symmetries that determine which particles can interact with which forces. These symmetries aren't just mathematical conveniences, they're the fundamental principles that determine the structure of reality. For example, the electromagnetic force exists because of a symmetry called U1 gauge invariance. This symmetry says that you can change the phase of the quantum wave function at every point in space and time, and the physics remains unchanged. This might sound abstract, but this symmetry is why electric charge is conserved and why photons exist. The weak nuclear force comes from a different symmetry called SU2, and the strong force comes from SU3 symmetry. The mathematical structure of these symmetries determines not just which particles exist, but also how they interact with each other. But here's where it gets really interesting. In the 1960s, physicists discovered that some of these symmetries can be spontaneously broken. This means that while the underlying laws of physics have the symmetry, the actual state of the universe doesn't. The most famous example is the Higgs mechanism, which we mentioned earlier. The laws of physics treat all particles equally. They all should be massless and travel at the speed of light. But the Higgs field breaks this symmetry by filling all of space with a non-zero value. Particles that interact with this field get slowed down and acquire mass, while particles that don't interact with it remain massless. This breaking of symmetry is what allows the rich variety of particles we observe. Without it, there would be only massless particles zipping around at the speed of light, and complex structures like atoms, molecules, and living beings couldn't exist. The concept of broken symmetry extends far beyond particle physics. It's responsible for the formation of crystals, the emergence of magnetism, and even the structure of the universe itself. In the earliest moments after the Big Bang, the universe was in a highly symmetric state. As it cooled, various symmetries were broken, leading to the formation of the fundamental forces and particles we observe today: quantum entanglement and non-locality. Let's return to one of the most mind-bending aspects of quantum mechanics: entanglement. When particles become entangled, they form a single quantum system that can't be described as separate parts. Measuring one particle instantly affects its entangled partner, no matter how far apart they are. This non-local connection troubled Einstein so much that he spent the last decades of his life trying to prove it couldn't be real. Along with colleagues Boris Podolsky and Nathan Rosen, he proposed what's now known as the EPR paradox. They argued that if quantum mechanics allows instantaneous connections between distant particles, then either the theory is incomplete or it violates the principle that nothing can travel faster than light. Einstein believed that particles must have hidden variables, properties that determine the results of measurements but aren't described by quantum mechanics. These hidden variables would allow particles to appear connected while actually being completely independent, like two coins that always land on opposite sides because they were specially prepared that way. But in the 1960s, physicist John Bell proved that any theory with hidden variables must make predictions that differ from quantum mechanics in specific, testable ways. Bell's theorem showed that you could design experiments to determine whether the correlations between entangled particles come from hidden variables or from genuine quantum non-locality. When these experiments were finally performed in the 1970s and 80s, the results were clear. Quantum mechanics was right and hidden variables were wrong. The correlations between entangled particles are stronger than any classical theory allows. Einstein's spooky action at a distance is real, but this raises a paradox. If measuring one particle instantly affects its entangled partner, why doesn't this allow faster than light communication? The answer lies in the random nature of quantum measurements. While the correlations between entangled particles are stronger than classically possible, you can't use entanglement to send information because the results of individual measurements are random. Imagine you have two entangled particles, and your friend takes one to another galaxy. When you measure your particle, you get a random result. Sometimes it's spinning up, sometimes down, with no way to control which. Your measurement instantly affects your friend's particle, but since your friend also gets random results, neither of you can tell whether the other has made a measurement until you compare notes later using ordinary, slower-than-light communication. This limitation is built into the structure of quantum mechanics. It's called the no communication theorem, and it ensures that quantum entanglement doesn't violate Einstein's relativity theory, even though it does create non-local correlations that Einstein found deeply troubling. Decoherence and the emergence of classical reality. If the quantum world is so strange and counterintuitive, why does the everyday world seem so normal and predictable? Why don't we see macroscopic objects existing in superpositions or becoming entangled with each other? The answer lies in a process called decoherence. When a quantum system interacts with its environment, which is inevitable for any real system, the delicate quantum superpositions and entanglements quickly get scrambled and lost. The system decoheres from a quantum superposition into a classical mixture of definite states. Here's how it works. Imagine a particle in a superposition of spinning up and down. In isolation, this superposition can persist indefinitely. But if the particle interacts with even a single photon from the surrounding environment, that interaction entangles the particle with the photon. The superposition still exists, but it's now spread across the particle-photon system in a way that makes it impossible to detect the quantum behavior of the particle alone. As more and more environmental particles interact with the system, the entanglement spreads further and further, creating what physicists call an entanglement web. The quantum information doesn't disappear, but it becomes distributed among so many particles that it's effectively lost from any practical perspective. This process happens incredibly quickly for macroscopic objects. A dust grain floating in air loses its quantum coherence in about 1031 seconds due to collisions with air molecules. A human being would decohere in about 1040 seconds just from interactions with the cosmic microwave background radiation left over from the Big Bang. Decoherence explains why we don't see quantum superpositions in everyday life, but it doesn't solve the measurement problem completely. We still don't know exactly how or when the transition from quantum possibilities to classical certainties occurs. Different interpretations of quantum mechanics give different answers to this question. But decoherence does show us something important about the relationship between the quantum and classical worlds. Classical reality isn't separate from quantum reality. It emerges from quantum reality through the unavoidable process of environmental interaction. The solid, predictable world we experience is actually a collective illusion created by the impossibility of isolating macroscopic objects from their quantum environment. Quantum biology, life at the quantum scale. For most of the history of quantum mechanics, biologists assumed that living systems were too warm, wet, and noisy to exhibit quantum effects. The delicate quantum superpositions and entanglements that we see in carefully controlled laboratory experiments would surely be destroyed instantly in the chaotic environment of a living cell. But in recent years, we've discovered that life has learned to harness quantum mechanics in sophisticated ways. Evolution has found methods to protect and utilize quantum effects even in biological systems. One of the most striking examples is photosynthesis, the process by which plants convert sunlight into chemical energy. When a photon hits a chlorophyll molecule in a leaf, it creates an excited electron that needs to find its way to the reaction center where photosynthesis actually occurs. In a classical system, this electron would randomly wander around, often getting lost and wasting the energy. But experiments have shown that plants use quantum superposition to solve this problem. The excited electron exists in a superposition of all possible paths to the reaction center simultaneously. It can sample all the routes at once and automatically take the most efficient path. This quantum coherence persists for hundreds of femtoseconds, far longer than anyone thought possible in a biological system. This quantum-enhanced efficiency might explain why photosynthesis is so remarkably effective. Plants convert sunlight to chemical energy with near-perfect efficiency, far better than our best artificial solar cells. They've evolved quantum computers that have been running for billions of years. But photosynthesis isn't the only biological process that uses quantum mechanics. Bird navigation appears to rely on quantum entanglement in special proteins in their eyes. These proteins contain pairs of entangled electrons that are affected by magnetic fields in different ways depending on their orientation. This creates a kind of quantum compass that allows birds to literally see the Earth's magnetic field. The sense of smell might also be quantum mechanical. One theory suggests that our noses can distinguish between molecules that have the same shape but different vibrational frequencies. This would require quantum tunneling of electrons through the molecular bonds, a purely quantum effect that allows particles to pass through barriers that should be impossible to cross classically. Even more speculatively, some researchers have suggested that consciousness itself might rely on quantum effects in microtubules inside neurons. While this idea remains highly controversial, it raises fascinating questions about the relationship between quantum mechanics and the mind. These discoveries are revolutionizing our understanding of biology. Life isn't just compatible with quantum mechanics, it depends on it. The quantum world isn't separate from the biological world. It's the foundation that makes biology possible. The information paradox in black holes. Black holes represent one of the most extreme environments in the universe, where gravity becomes so strong that not even light can escape. But they also represent one of the deepest puzzles in theoretical physics, a place where quantum mechanics and general relativity come into direct conflict. The problem begins with Hawking radiation, discovered by Stephen Hawking in 1974. Using quantum field theory in curved space-time, Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This radiation causes black holes to slowly evaporate, eventually disappearing completely. But this creates a paradox. The matter that falls into a black hole carries information, the quantum states of all the particles involved. If the black hole eventually evaporates completely, what happens to this information? According to general relativity, it's destroyed when the black hole disappears. But according to quantum mechanics, information can never be destroyed. It can only be scrambled or transferred somewhere else. This contradiction has driven decades of research into the fundamental nature of information, space, and time. Various solutions have been proposed, each with radical implications for our understanding of reality. One possibility is that information is somehow encoded on the surface of the black hole rather than in its interior. This idea, called the holographic principle, suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, like a hologram. If this is correct, it would mean that our three-dimensional reality might be a projection from information stored on a distant two-dimensional surface. The universe might be fundamentally two-dimensional, with the third dimension being an emergent illusion. Another proposed solution involves the idea of black hole complementarity. According to this view, information both falls into the black hole and is emitted in the Hawking radiation, but no single observer can ever see both perspectives simultaneously. It's like a cosmic version of the wave-particle duality. The information is both inside and outside the black hole, depending on your perspective. More recently, some physicists have proposed that black holes might be connected to other regions of space-time through wormholes, tunnels through space and time that could allow information to escape from the black hole interior and appear somewhere else in the universe. These ideas push the boundaries of our understanding of space, time, and causality. They suggest that the universe might be far stranger and more interconnected than we ever imagined. Quantum gravity and the theory of everything. Perhaps the biggest challenge in modern physics is developing a theory of quantum gravity, a framework that can describe how gravity works at the quantum level. General relativity treats gravity as the curvature of space-time, while quantum mechanics describes the other forces as exchanges of virtual particles. These two approaches seem fundamentally incompatible. At the Planck scale, where quantum effects of gravity become important, our current theories break down completely. We need a new framework that can unify quantum mechanics and general relativity into a single, coherent description of reality. The leading candidate for such a theory is string theory, which proposes that the fundamental constituents of reality aren't point particles but tiny, vibrating strings. Different vibration patterns of these strings correspond to different particles, electrons, quarks, photons, and even gravitons. String theory naturally includes gravity and suggests that all the fundamental forces might be different aspects of a single, unified force. It also predicts the existence of extra dimensions of space, which could help explain some of the mysteries of particle physics and cosmology. But string theory comes with its own puzzles. It requires at least 6 extra dimensions beyond the 3 spatial dimensions we experience. These extra dimensions would need to be compactified, curled up so small that we can't detect them directly. The way these dimensions are curled up would determine the properties of particles and forces in our 3-dimensional world. The problem is that there are an enormous number of ways to curl up the extra dimensions, possibly 500 different possibilities or more. This is called the landscape problem. With so many possible versions of string theory, how do we determine which one describes our universe? Some physicists have embraced this abundance of possibilities, suggesting that all of them might be realized in different regions of a vast multiverse. Our universe would be just one bubble in an infinite cosmic foam, each bubble with its own laws of physics determined by how its extra dimensions are configured. Others are pursuing alternative approaches to quantum gravity. Loop quantum gravity suggests that space itself is made of tiny, discrete loops at the Planck scale. In this theory, space has a granular structure like a cosmic mesh, and time might come in discrete ticks like frames in a movie. Another approach, called causal set theory, proposes that space-time is made of discrete points connected by causal relationships, essentially a quantum version of the idea that space and time are made of atoms. Emergent gravity theories suggest that gravity might not be fundamental at all, but rather an emergent phenomenon arising from more basic quantum information processes. In these theories, space-time itself emerges from quantum entanglement, and gravity is a manifestation of the flow of quantum information. The anthropic principle and the multiverse, the fine-tuning of the fundamental constants raises profound questions about the nature of reality and our place in it. Why do the laws of physics seem so perfectly calibrated to allow the existence of complex structures and life? One answer is the anthropic principle, which comes in several forms. The weak anthropic principle simply observes that we shouldn't be surprised to find ourselves in a universe compatible with our existence. After all, we couldn't exist in a universe with very different physical laws. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. This is more controversial because it seems to imply that the universe was somehow designed for life. But there's a third possibility that avoids the implications of design, the multiverse hypothesis. If there are many universes with different values of the fundamental constants, then some of them will inevitably have the right properties for life. We find ourselves in such a universe simply because we couldn't exist in the others. The multiverse idea appears in several different contexts in modern physics. In cosmology, inflation theory suggests that our observable universe is just one bubble in an eternally inflating cosmic foam. Each bubble would have different physical properties, determined by how the fundamental fields happen to configure themselves during inflation. In quantum mechanics, the many worlds interpretation suggests that every quantum measurement splits the universe into multiple branches, each representing a different possible outcome. The multiverse would contain all possible histories of the universe, including many where you made different choices or where the fundamental constants have different values. In string theory, the landscape of possible extra-dimensional configurations could correspond to different universes with different laws of physics. If all these configurations are realized somewhere in the multiverse, then our particular set of physical laws would be just one possibility among countless others. But the multiverse hypothesis raises its own philosophical problems. If there are infinitely many universes, then everything that can happen does happen somewhere. There would be universes where dinosaurs never went extinct, where the laws of physics are completely different, where you became a famous scientist or artist or athlete. This leads to puzzles about probability and prediction. If every possible outcome occurs in some universe, what does it mean to say that one outcome is more likely than another? How can we make testable predictions if every prediction is correct somewhere in the multiverse? Quantum computing and the future of information. As we've learned to understand and manipulate quantum systems, we've begun to develop technologies that harness the full strangeness of the quantum world. Quantum computers represent perhaps the most dramatic example of this quantum revolution. Classical computers process information using bits that are either 0 or 1. But quantum computers use qubits that can exist in superpositions of both 0 and 1 simultaneously. This allows quantum computers to explore many possible solutions to a problem in parallel, potentially solving certain types of problems exponentially faster than classical computers. The potential applications are staggering. Quantum computers could break most of the cryptographic systems that currently protect our digital communications. The RSA encryption that secures online banking and e-commerce relies on the difficulty of factoring large numbers, a problem that would be easy for a sufficiently powerful quantum computer. But quantum computing also offers new opportunities for ultra-secure communication. Quantum key distribution uses the principles of quantum mechanics to create communication channels that are fundamentally unbreakable. Any attempt to intercept the quantum signals inevitably disturbs them, alerting the sender and receiver to the presence of an eavesdropper. Quantum computers could also revolutionize our understanding of complex systems. They could simulate the behavior of large molecules, leading to breakthroughs in drug discovery and materials science. They could model the quantum mechanics of high-temperature superconductors, potentially leading to room-temperature superconductivity and transforming energy transmission and storage. In artificial intelligence, quantum computers might be able to recognize patterns and solve optimization problems that are impossible for classical computers. They could help us understand the quantum mechanics of photosynthesis and other biological processes, leading to more efficient solar cells and artificial photosynthesis systems. But building practical quantum computers is incredibly challenging. Qubits are extremely fragile. Any interaction with the environment can destroy the delicate quantum superpositions that make quantum computing possible. Current quantum computers can only maintain coherence for microseconds before environmental noise destroys their quantum properties. Researchers are exploring many different approaches to building robust quantum computers. Some use superconducting circuits cooled to temperatures colder than deep space. Others use trapped ions manipulated by precise laser pulses. Still others use photons, particles of light, that are naturally resistant to environmental interference. The role of consciousness and observation. One of the most debated aspects of quantum mechanics is the role of consciousness and observation in determining physical reality. The measurement problem, how and when quantum superpositions collapse into definite states, has led some physicists to suggest that consciousness plays a fundamental role in quantum mechanics. This idea traces back to the founders of quantum mechanics themselves. Werner Heisenberg wrote, "What we observe is not nature itself, but nature exposed to our method of questioning." John Wheeler proposed that the universe might be participatory, that observers don't just discover pre-existing reality, but actually help create it through their observations. The most famous example is Schrödinger's cat, a thought experiment designed to show the absurdity of applying quantum mechanics to macroscopic objects. A cat is placed in a box with a quantum system that has a 50% chance of triggering a poison mechanism. According to quantum mechanics, before anyone opens the box, the quantum system exists in a superposition of both outcomes, which would seem to imply that the cat is both alive and dead simultaneously. Some interpretations of quantum mechanics suggest that the cat remains in this superposition until a conscious observer opens the box and makes a measurement. The act of conscious observation is what causes the superposition to collapse into one definite outcome. But this interpretation raises more questions than it answers. What counts as consciousness? Would a simple recording device cause the collapse, or does it require a sentient observer? Where do you draw the line between conscious and unconscious systems? Most physicists today reject the idea that consciousness plays a special role in quantum mechanics. The process of decoherence, which we discussed earlier, provides a mechanism for the emergence of classical reality that doesn't require conscious observers. Any interaction with the environment, conscious or not, can cause quantum superpositions to decohere. But the relationship between quantum mechanics and consciousness remains an active area of research. Some scientists have proposed that consciousness itself might be a quantum phenomenon emerging from quantum processes in the brain. While these ideas remain highly speculative, they raise fascinating questions about the nature of mind and reality, experimental tests, and future discoveries. As we push the boundaries of quantum mechanics to smaller and smaller scales, we're developing new experimental techniques that allow us to test our theories in unprecedented ways. Particle accelerators like the Large Hadron Collider can create conditions that existed microseconds after the Big Bang, allowing us to probe the fundamental structure of matter and energy. Future experiments will push even further into the unknown. Proposed particle accelerators would dwarf the LHC in size and energy, potentially reaching scales where new physics becomes visible. These machines might discover supersymmetric particles, extra dimensions, or entirely new types of matter and forces. Gravitational wave detectors like LIGO have opened a new window into the universe, allowing us to observe the collision of black holes and neutron stars. Future detectors will be even more sensitive, potentially allowing us to see the gravitational waves produced by the Big Bang itself or by the collision of primordial black holes from the early universe. Space-based experiments will take advantage of the ultra-high vacuum and low temperatures of outer space to create conditions impossible to achieve on Earth. These experiments might allow us to test the equivalence principle, the foundation of general relativity, with unprecedented precision, or to search for dark matter particles through their extremely rare interactions with ordinary matter. Quantum technologies will continue to advance, potentially leading to quantum computers capable of solving problems that are intractable for classical computers. These machines might help us simulate complex quantum systems, leading to breakthroughs in our understanding of high-temperature superconductivity, quantum magnetism, and other exotic phases of matter. But perhaps the most important discoveries will come from experiments we haven't even imagined yet. The history of physics is full of unexpected discoveries that opened entirely new fields of research. The discovery of radioactivity, X-rays, and cosmic rays all came as surprises that revolutionized our understanding of nature. As we develop more sensitive instruments and more sophisticated theoretical frameworks, we may discover phenomena that challenge our most basic assumptions about reality. We might find that space and time have a granular structure at the Planck scale, or that information can travel faster than light in certain quantum systems, or that consciousness plays a more fundamental role in physics than we currently believe. Philosophical implications. The quantum revolution has profound implications for philosophy and our understanding of reality. The classical worldview, which dominated science for centuries, assumed that the world consists of objects with definite properties that exist independently of observation. Quantum mechanics challenges all of these assumptions. The principle of superposition suggests that particles can exist in multiple states simultaneously until measured. This challenges our intuitive notion of definite properties. The uncertainty principle shows that there are fundamental limits to what can be known about a system, suggesting that reality might be inherently indeterminate rather than just unknown. Quantum entanglement demonstrates that widely separated particles can be correlated in ways that seem to transcend space and time. This challenges our notion of locality, the idea that objects are only directly influenced by their immediate surroundings. The measurement problem raises questions about the role of observation in determining reality. Does measurement create reality or merely reveal it? Is there an objective reality independent of observers, or does reality emerge from the interaction between systems and their environment? These questions have led philosophers to develop new frameworks for understanding the nature of reality. Some embrace a relational view, where properties of objects exist only in relation to other objects or observers. Others propose that reality is fundamentally informational, with matter and energy being different aspects of information processing. The multiverse hypothesis raises its own philosophical questions. If there are infinitely many universes, what makes our experience special? Is there any meaningful sense in which we could have been different? Or are all possible versions of us equally real? These aren't just abstract philosophical puzzles. They touch on deep questions about the nature of existence, identity, and meaning. If reality is fundamentally quantum mechanical, what does this mean for free will, consciousness, and moral responsibility? But here's the truly mind-blowing realization that brings everything together. We may never find the ultimate building block of reality because the question itself might be fundamentally wrong. Think about everything we've discovered. Every time we thought we found the smallest, most fundamental thing, it turned out to be made of something smaller. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks, and quarks might contain even smaller structures. But what if this hierarchy doesn't end with some ultimate particle? What if reality is like an infinite Russian nesting doll, with smaller and smaller structures all the way down? Or even more radically, what if the very concept of size breaks down at the smallest scales? We've seen that space and time themselves might be quantized at the Planck scale. Below that level, our normal concepts of distance, duration, and even causality might no longer apply. Maybe reality isn't built from building blocks at all. Maybe it emerges from relationships, from information, from the quantum foam of virtual particles popping in and out of existence. Maybe the universe is more like a vast computation than a construction made of parts. This is the deepest lesson of quantum mechanics. Reality is far stranger and more wonderful than our everyday experience suggests. The solid world around you is mostly empty space. The particles that make up your body are constantly fluctuating in and out of existence. The forces that hold everything together are carried by invisible messengers that exist only for the briefest moments. You are not a collection of separate atoms, but a pattern of quantum fields, constantly exchanging information with the quantum vacuum that fills all of space. The boundaries between you and the rest of the universe are far more fluid than you might imagine. And this brings us to perhaps the most profound realization of all. The quest to find the smallest building block of reality has taught us that we are intimately connected to the cosmos in ways our ancestors could never have imagined. The carbon in your body was forged in the core of a dying star. The calcium in your bones was created in a supernova explosion. The iron in your blood was scattered across the galaxy by stellar winds and then swept up into the cloud of gas and dust that eventually became our solar system. But it goes deeper than that. The quantum fields that make up your body are the same fields that fill all of space and time. In a very real sense, you are a temporary pattern in the universal quantum field, a brief note in the cosmic symphony that has been playing for 13.8 billion years. So, how small is the universe's smallest building block? The answer is that we may never know, not because our instruments aren't sensitive enough, but because the question assumes a classical view of reality that quantum mechanics has shown to be fundamentally incorrect. Instead of building blocks, we have quantum fields. Instead of definite properties, we have superpositions and probabilities. Instead of separate objects, we have entangled systems that transcend space and time. The journey to understand the smallest scales of reality has taught us that the universe is far more mysterious, interconnected, and beautiful than we ever imagined. We've discovered that empty space teems with virtual particles, that particles can be in multiple places at once, that information might be more fundamental than matter and energy, and that consciousness and reality might be more intimately connected than we ever suspected. But perhaps, most importantly, we've learned that the quest for knowledge is never-ending. Every answer reveals new questions. Every discovery opens new mysteries. And that's not a limitation. It's the most wonderful thing about science and about being human. We are conscious arrangements of quantum fields trying to understand our own fundamental nature. We are the universe becoming aware of itself. And that awareness, that curiosity, that drive to understand, that might be the most remarkable phenomenon in all of physics. The smallest building blocks of reality might not be particles or strings or loops of space-time. They might be the questions we ask, the connections we make, and the wonder we feel when we contemplate the infinite depth and beauty of the cosmos. And that wonder, that curiosity, that determination to keep asking, what if? And how does this work? That's something worth holding on to as we continue this incredible journey of discovery together. If this journey through the quantum realm has sparked your curiosity about the deepest mysteries of reality, there's so much more to explore. Check out the next video where we'll dive into how these quantum effects might be creating parallel universes right now.